decreasing. At a potential of approximately 1V, the resistance of the emitter-collector line is decreasing clearly by what the LED connected in parallel to the transistor is turned off. The resistance and so the voltage across the emitter-collector line becomes minimal if the potential at the input clamps equals the supply voltage of the circuit. The series resistors connected to the base pins are limiting the base current. In contrast, the resistance of the PNP transistors is minimal whenever the potential between ground and X1 respectively X3 is 0V, while it is maximal if the potential at the input clamps equals the supply voltage. The LED gets lighted up at a potential of approximately 4.3V, the transistor is turned off. When connecting X1 and X2 to ground, respectively X3 and X4 to the positive supply voltage, the resistance of transistor 2 and 3 is at its maximum, while those of transistor 1 and 4 is at its minimum. As a result, the potential at the midpoint of the left leg is 4.1V, while those at the midpoint of the right leg is 0.6V. In sum, there is a difference in potential of 3.5V between the two midpoints of the H-bridge. If a load is connected between the two midpoints, a current is running from the positive terminal via transistor 1, from the left to the right midpoint through the load, and finally via transistor 4 to the negative terminal. The situation alters if X1 and X2 are connected to the positive terminal, while X3 and X4 are connected to ground. Now transistor 1 and 4 are turned off, while transistor 2 and 3 are turned on, hence the positive terminal is at the right side of the load. If all 4 clamps are connected to ground, the upper PNP transistors are turned on, while the lower NPN types are turned off. The potential at both midpoints of the bridge equals nearly the positive supply voltage, which is why no current is running through the load. If all clamps are connected to the positive terminal of the supply voltage, the upper PNP transistors are turned off, while the lower NPN types are turned on. The potential at both midpoints is nearly 0V, hence there is also no current running through the load. When composing an H-bridge of bipolar junction transistors, the base current required to bring the transistors into saturation mode has to be considered. The dimensions of R1 to R4 depend on the supply voltage. The resistance value has to be doubled when operating the circuit with an input voltage of 12V instead of 6V. Using N-channel respectively P-channel MOSFETs instead of NPN or PNP types gives you some benefits. Just 4 pull-up or pull-down resistors are required and the values of R1 to R4 are not critical, simply use the relative high values to avoid operating near the maximal power dissipation. The minimal input voltage of the circuit is affected by the source gate voltage required to turn the MOSFETs reliably on. It must be clearly higher than the threshold voltage. The 3.3V supply voltage used here are not sufficient to turn the transistors fully on. When using an input voltage of 5V, the transistors are turning on reliably. And when using 12V, the potential between the clamps of the load is sufficient to turn the electric motor. An H-bridge is often composed with just 2 input clamps to reduce the number of required control pins. The potential at the input clamps is pulled to ground by 2 resistors, by what the low side transistors are turned off, while the high side transistors are turned on. No current is running through the load. If the right input clamp is connected to the positive terminal, transistor 1 and 4 are turned on, and the positive pole is at the left side of the load. If the left input clamp is connected to the positive terminal, transistor 2 and 3 are turned on, and the positive pole is at the right side of the load. If both clamps are connected to the positive terminal, the low side transistors are turned on, and once more no current is running through the load. A disadvantage of those simple control is that there is no way to turn all 4 transistors simultaneously off. The maximal supply voltage should be clearly below the maximal source gate voltage to avoid operating at the limit. Keep voltage peaks in mind when switching inductive loads. If the supply voltage exceeds the maximal source gate voltage of the MOSFETs, 4 voltage dividers, each composed of a Zener diode and a constant resistor, should be inserted. The Zener voltage must be clearly higher than the threshold voltage required to turn the transistors on. Now, the maximal source drain voltage, which is usually significantly higher than the maximal source gate voltage, limits the input voltage of the circuit. The clamps must always be connected to either the positive or the negative supply voltage. Here, the left input clamp is connected to the positive terminal of the voltage source, by what transistor 1 is turned off completely, while number 2 is turned on completely. The voltage at the right input clamp is 0V, by what transistor 3 is turned on and transistor 4 is turned off. The voltage at the right clamp is increasing slowly. At a potential of approximately 1.8V, the threshold at the gate of transistor 4 is reached, consequently the resistance of its source drain line is decreasing. Between source and gate of transistor 3 there is a voltage drop of approximately -10V, hence those device is still turned on. The current running through the right leg of the H-bridge is increasing clearly. The electric power dissipated by transistor 4 is increasing too, which is why this device is heating up strongly in just some seconds. If the voltage at the right input clamp would be kept at a level of 2V, the H-bridge would be destroyed in just some seconds. If half of the input voltage is applied to the right input clamp, the current is increasing to almost 5A for a short span of time, until the power source cuts off the supply voltage automatically. During a switching operation of the H-bridge, meaning whenever the potential at one of the clamps alters from the positive supply voltage to 0V or vice versa, there is always a high current running through the legs of the circuit for a short span of time. The overlapping turn-on time is called cross-conduction or shoot-through. If the bridges are actuated manually, like seen at this video, the switching operations are relatively slow, and caused by contact bounce, the bridges get switched several times in quick succession. Both effects cause high currents running through the legs of the H-bridge, which may destroy the circuit. While recording the sequences of this video, I have smoked more than just one transistor. Mostly the devices are destroyed in pair. The input clamps of an H-bridge should always be connected to the input circuit before turning on the supply voltage. Moreover, the slew rate of the input signal should be as high as possible. A turn-on delay implemented by a linear RC circuit prevents the H-bridge from a shoot-through. Whenever the voltage at X1 alters from the positive supply voltage to 0V, capacitor 1 gets charged slowly via resistor 1, hence the turn-on procedure of transistor 1 is delayed. In contrast, capacitor 2 gets discharged quickly through diode 2, which is forward biased, hence transistor 2 is turned off with almost no delay. There is always a small capacitance at the gate area of MOSFETs, so the external capacitors could eventually be omitted. R5 and R6 are pull-down resistors. The high-side MOSFET is turned off immediately, observable by the yellow curve, because the discharging current of capacitor 1 is running through the forward biased diode number 1. The turn-on procedure of the low-side MOSFET is delayed, because the charging current of capacitor 2 is running through resistor number 2. At the falling edge of the input signal, the turn-off procedure of the low-side MOSFET, marked by the green curve, is faster than the turn-on procedure of the high-side MOSFET, because now diode number 2 is forward biased. In slow motion you can see that both transistors are turned off simultaneously for a short span of time. The RC circuit impedes the overlapping turn-on